This is the 10th video in IB Astrophysics. We're going to be looking at cosmology in this one. In the last video, we looked at some ways to measure the distances to far galaxies, associated variables, type 1a supernova, other standard candles. And among other things, we're going to use that in this video. But first, we're going to go back to Isaac Newton and what he thought about the universe. And this is called Newton's model, although Newton didn't come up with it, and he was not even one of its most important proponents. It was just he was famous, so they named it after him. Newton's model of the universe is that the universe is infinite and more or less static. In other words, the universe looks approximately the same now as it did 10,000 years ago, and it looks approximately the same a billion years ago. And in a billion years, it will still look approximately the same. Some stars will have moved, some stars will have died, some new stars will have been created, but the overall picture of the universe will be about the same. There is a problem with this, though. And it was first recognized almost as soon as this particular model of the universe became widespread among astronomers. And that is that if the universe were infinite, the sky wouldn't be dark. The reason is because if the universe were infinite, then any direction you look, you would see a star. And there wouldn't be any dark parts of the sky at all. And the entire sky would look like something like the Milky Way does, as just light everywhere. That's referred to as Olber's paradox, which is actually a lot more complicated than that. If you're interested, I encourage you to Google it. The Wikipedia page on Olber's paradox is actually really useful. But basically, Olber's paradox is if the universe was infinite, the sky wouldn't be dark because there'd be a star everywhere you look. Now, a number of solutions have been suggested, but the most probable one is that the universe is neither infinitely large, nor, and this is important, infinitely old. Because if the universe is not infinitely old, that means light from very distant parts of the universe hasn't yet reached us. And so we wouldn't see stars that are more than a certain number of light years away. But there's another problem with Newton's model, and that is that distant galaxies are moving away from us, which happens because, and we know that because the light from them is redshifted. Remember from waves, the Doppler effect, light from a moving source is observed at a lower frequency. And so because the galaxy's light is more red than it should be, that tells us that the galaxy is moving away from us. And the equation we use is V equals delta F over F times C. The speed at which the galaxy moves is equal to the change in frequency divided by the original frequency of the light times the speed of light, c. That equation is in your equation sheet, but you need to know that that's the Doppler shift equation for light. And Edwin Hubble, in the, I believe, the 30s, who was the one who discovered that these distant galaxies are moving away, made a graph where he plotted the speed of the galaxies on the y-axis and their distance on the x-axis. And the graph he got looked like this. Approximately linear. Now there's a lot of scatter in it, mainly because of the difficulty in measuring the distance to faraway galaxies, but it is definitely linear, things that are farther away are moving faster. And the slope of that line is something called the Hubble constant, or h naught. The current best estimate of the Hubble constant is about 72 kilometers per second per megaparsec. What that means is that a galaxy that is 1 megaparsec, meaning 3 million light years away, is going to be moving away from us at a speed of about 72 kilometers per second. And a galaxy that is 100 megaparsecs away would be moving 7,200 kilometers per second away from us. So for an exercise, let's estimate the distance to a galaxy that is moving away from Earth at a speed of 130 kilometers per second. So h naught equals v over d is the equation. That's a statement of Hubble's law. d equals v over h naught. 130 divided by 72 gives us a distance of 1.8 megaparsecs, which is not quite 6 million light years. So Hubble's law, fairly straightforward to state. Now the question is, what are the implications of Hubble's law? And that is that the universe is expanding. Now all the galaxies are moving away from us, but the farther ones are moving even faster, which implies that space is, in some sense, stretching. If you blow up a balloon, you'll find that 2 points that start out close to each other will move away from each other, but they'll do so slowly. Whereas 2 points that start out far away from each other will also move away from each other, but they'll do so more rapidly. And you need to be able to explain why Hubble's law indicates the universe is expanding. And very common misconception, it's not like the universe is expanding into a vacuum, in which case there would be an edge to the universe. We're pretty sure that's not the case. But instead, space itself is expanding. Again, the balloon metaphor. Space is not like the interior of the balloon, it's like the exterior of the balloon. The balloon, or the balloon's surface, does not have an edge. It's finite. You can calculate its surface area. If it's a sphere, the surface area is 4 pi r squared. But it doesn't have an edge. It's not expanding into anything. And so if you think of the universe as like the surface of a balloon, I mean, a different number of dimensions and all that, but same basic idea. That will be the best way to think about it. The Hubble constant also gives us a useful way to estimate the age of the universe. Now, if we imagine a star or a galaxy that has been moving away from us for a time t, okay, so a galaxy has moved a distance d at speed v, that's assuming constant speed, of course. The amount of time it's taken to get there is d over v. But remember, the Hubble constant says that h naught equals v over d, and so the amount of time the galaxy has been moving away from us equals the reciprocal of the Hubble constant, which, if you mess with the weird units, works out to be about 13.5 billion years at our best estimate. Now this does assume that the speed has been constant, which is probably not a great assumption, but as a first order guess, or first order approximation to the age of the universe, this is not bad. And there are other methods that we have of measuring the age of the universe, mainly having to do with globular clusters and white dwarfs. They're interesting but not part of IB, that confirm that the age of the universe is somewhere in that range, in the tens of billions of years. What you need to know is what Hubble's law is, what Olber's paradox is, how we can tell the universe is expanding, and how to use Hubble's law to estimate the age of the universe.